Hey everybody, I wanted to spend a little bit of time on this video talking about quantum theory, which is pretty much the theory of everything that has to do with an atom. Okay, and the quantum theory was a pretty recent theory devised in the early to mid 1900s. So, I mean, that's very recent compared to some of the other um, things that are going on, or some of the other things that we know in chemistry. And I will also say that quantum theory is very difficult. There's a lot of upper level math involved and differential equations and things like that. So this really is to serve as kind of an introduction to some of the more basic, straightforward concepts. And by the end, you should get a good idea of what quantum theory is, and that B, it goes a lot deeper than what I'm going to say here. So, so let's talk a little bit about it. Quantum theory was kind of developed over time and was contributed to by a lot of famous physicists and chemists. Okay, and this is not by any stretch of the imagination an all-encompassing list. This is just maybe some of the more famous or bigger players. And so Max Planck, he kind of started the idea, maybe not is the best word to use, but he developed this formula here where energy is related to the frequency, okay? And that's the frequency of a wavelength of energy. Excuse me. And so, the frequency, how often that wave passes a given point. Okay, and this one has this has a greater frequency because as it's moving, more waves will pass this given point. More on that later, but the greater the frequency, the greater the energy. But what Max Planck also figured out, Max Planck, if you're a German scholar, is that the energy to make electrons emit photons, okay, is what we call quantized. Okay, he was the first to realize that if an electron is going to get excited, so it starts here in maybe the 1s, and then we want to excite it into the 2s. If we're going to move that electron from here to here, it takes a certain amount of energy. Okay, if that energy, and I'm going to leave units off of it even, if that energy is 3, but we only give it 2.5, it's not going to get up here. Okay, it's not going to do it. You're required to have the exact amount of energy that the electron needs in order to excite the electron correctly. And so you may know that atoms have electrons that can move around. And so this transition, and I'll make it the transition from the electron here to here takes a certain amount of energy, and from here to here takes a certain amount of energy. An electron can't be here. It can't be in the middle somewhere. It can't be here. Okay, it has to be here or here. Okay, that is what Max Planck figured out, is that the energy required to excite electrons is quantized. Okay, and so then Einstein came along after Max Planck. They may have been contemporaries, but Einstein, among his millions of other things that he did, came up with he's the one that kind of named the photoelectric effect. And so metals in particular can release what we call photons. Okay, and so photons are the things that make up light, okay, or other forms of electromagnetic radiation, things like infrared waves or UV, okay. And so you can shine a light, sunlight, let's say, onto a metal, and sometimes that metal will release a photon of energy. Okay? Now, relate this back to Max Planck. If that light that hits the metal is the correct frequency, okay, you can excite an electron, and that electron then releases photons. Okay? And then also as a result of this, Einstein kind of figured out that photons act like waves sometimes, and photons also act like particles. Okay, so this is called the wave-particle duality, where photons, or all electromagnetic radiation, sometimes moves as a wave, okay, and then sometimes moves as particles going in this direction. Okay, so let me break every rule of screencasting and flipped teaching and go back and review a little bit, because I think it's important to summarize here. Okay, now when an electron is excited, when it goes from the ground state and is excited to an excited state, that takes energy. And then when the electron relaxes and moves back down, it releases energy in the form of photons. Okay, that's what Planck characterized, E equals h nu, the energy it takes for one of these transitions. Okay, and then Einstein realized that as you shine specific wavelengths or frequencies of lights onto metals, then this can create this transition, okay, this excitation-relaxation cycle, and release those photons as well. Okay, and so he also then figured out wave-particle duality. Okay, so then Niels Bohr comes along, and Bohr is looking through a spectroscope, and he takes a spectroscope which takes white light and it separates white light into its component colors. Okay, and we've seen this before in the sky after it rains. We end up with a rainbow in the sky, right? And then it's red, orange, yellow, green, blue, indigo, violet. Okay, and we see light reflecting and diffracting and doing all the things that light does into a rainbow. Okay, well, you have a device that can do that, and that's called a spectroscope. If we hold it up to the sun or do it from some other white light source, not a specific light source, you end up getting a continuous spectrum. You end up getting a rainbow. Okay, what he did is he took specific elements, like let's say neon, and when he took neon, because it's only one element, and because it's only one element, it has only one specific pattern of electrons. Remember, it takes a specific amount of energy to excite an electron, which relates to a frequency, right? What he saw was that those elements only gave a special pattern, because there was only certain electrons giving off certain amount of energy, and so each element has a unique pattern in what we call an emission spectra. Okay, this, for example, this way down here may I don't know exactly, and it's not important right now. That may be a 1s electron jumping up one level to the 2s. That takes a certain amount of energy. Okay, and it has to be a specific amount of energy. If it took many different types of energy, I think my example last was like a 3. If it could also use 2.5 and 2.4, okay, that means that this line would be wider. It would be more red in a broader spot. But because it's a single line, we know that it only takes a very specific amount of energy, because of Planck, specific frequency, to excite that light. So this is actually a proof that that the energy is quantized, that there's quanta of energy that that excites electrons, or that electrons move in specific quantities of energy throughout the atom. And so, just to summarize some of the things that happens, I probably said quantized a whole bunch of times. But not only is the energy of an electron quantized, that electron moving between energy levels, okay, but so are photons, okay. Photon gives off energy that is quantized, okay. Another thing is wave-particle duality. We're going to see that electrons behave as a wave. They can move as a wave, or they can travel as particles, and we kind of choose which one suits our needs at this level, okay. We're like, hey, it can be a particle. Great, done, okay. And the other thing, and we're going to do an experiment about this, is that the spectra, each element has a unique spectra. So if we have an unknown element, we can compare it to the known spectra of each element, and we can get that, okay. Other things that it gives is that all that electron configuration stuff where we have S, P, Ds, and Fs, okay, and then the electron probability. You can do all sorts of quantum mechanics, and you get the 90% probability. Here's the nucleus, and it's 90% likely to be found in a sphere, or maybe a p orbital that's, remember, 2 teardrops or whatever. Okay, and then there's all sorts of other crazy stuff, wave functions and Hamiltonian operators and all sorts of things that are way, way beyond this kind of introductory thing, okay, that come from quantum theory and quantum mechanics. Okay, so that's kind of a brief introduction to quantum mechanics and some of the people involved with quantum mechanics. So have a great day.